Hello, welcome to Basics of Finite Element Analysis. In the remaining part of this week, starting today, we will be discussing the beam theory and how it is analyzed using the finite element method. So, what we are going to discuss in detail is the Euler-Bernoulli beam. And in this particular beam theory, we say that suppose there is a beam and when it deflects, so it has a neutral axis, and when it bends, it bends in such a way. So, that is my, this is my undeformed thing and this is the green is my deformed, and it bends in such a way that the deformed, so in the original undeformed beam, the neutral axis was perpendicular to the edge of the beam, okay. And in the deformed beam, if this is a vertical plane, in the deformed beam also, the deformed neutral axis is perpendicular, it remains perpendicular to the edge of the beam. If edge of the beam was perpendicular earlier, it will continue to remain perpendicular in the deformed state also. So, a lot of times in literature you will see that they say that plane sections remain plane and normal after bending. Okay. So, this is a plane section and originally it was at 90 degrees to the neutral axis. After bending, it continues to remain a straight plane section, okay, and it also continues to remain at 90 degrees of perpendicular to the neutral axis. So, this type of a beam is known as Euler-Bernoulli beam, and this type of deformation is there when the beam is long. And what does long mean? That the length of the beam is very large compared to its thickness. So, this is, let us say overall thickness is B, I will call it some thickness T, then this is very large compared to T. For short beams or thicker beams, this may not be true. So, then Euler-Bernoulli assumption that plane sections remain plane and also normal, it may not necessarily be true. So, in the last lecture we will discuss a little bit about those beams also. So, the governing equation for this beam is d2 dx square b times d2w over dx square equals f of x. Let us look at what these parameters mean. So, suppose I have a beam and it is having some vertical load which is distributed in nature, then this distributed load I call it Fx. So, its units are Newton per meter of F, and B is a multiple of two things. One is Young's modulus and I is the moment of inertia of the cross section at point x. So, this I can vary with respect to x, and so could E. So could E. Couple of other things, because this is the convention we will use. So, if I have a small element of the beam which I just represent as a line, and let us say its nodes are 1 and 2, this is my x axis, then W is positive is if it is going up. So, this is W1 and this is W2, and if it is the eth element, I put superscript E. Okay. Similarly, the shear forces is, this is Q1E is the shear force at node 1, and this is at Q2, this is Q2E at node 2. And the, oh excuse me, I will actually call it Q3. So, you will wonder where did Q2 go. So, Q2 is the bending moment, and Q4 is moment at node 2. So, Q1 and Q3 represent shear forces, and Q2 and Q4 represent moments, and these moments are positive if they are clockwise, they are negative if they are anti-clockwise. So, W is the deflection of the beam, it is positive is going up, and if it is going down then it is negative, and Q's are shear forces and moments. And finally, so this is there. I will also like to mention about slopes at both the ends, but we will not discuss at this stage. So, if this is the convention, then if we have to develop a weak formulation using this governing differential equation, please note that this is a fourth order ordinary differential equation. So, if I have to develop a weak formulation, then I will have to integrate it in parts 2 times, right. So, I am going to integrate it over the domain of the element HE, and the error so this is the error. If there is, if the solution was exact, this would be 0, but here we are looking at approximate solution. So, this is the error, and I multiply by a weight function, and here I call my weight function as V. So, earlier we have called it W, but in context of beam W makes more sense in terms of deflection. So, I call it V, and then I integrate it over the domain and I equate it to 0. So, I do my integration by parts once, and I get 0 to HE minus dV over dx times B d2W over dx, and the entire thing is now differentiated only once, minus Vf dx, and then I get a boundary term plus V times d by dx B d2W over dx square I am evaluating it at 2 locations 0 and HE, and this entire thing becomes 0. So, this is integration by parts once, and I will do the integration by part one more time. So, now I get d2V over dx square times B times d2W over dx square minus Vf I integrate the entire thing, and then the boundary terms now have two boundary terms. One is V B W prime prime. So, this is same as the earlier term, and then the other term is V prime B W prime prime evaluated at 0 and HE, and this equals 0. Now, let us look at this equation in a little bit more of detail. So, this is my weak form. Okay. If I look at the boundary terms, I have now two boundary terms. One is V times the first derivative of B times W prime prime, and the second boundary term is V prime B W prime prime, right. In our earlier lectures, we had said that these boundary terms help us figure out what are the primary variables and what are the secondary variables. So, when I look at these terms, V, it helps us determine that one primary variable is W, and minus V prime, it helps us make a judgment that the other primary variable is minus W prime or minus dW over dx, right. Because we had said, discussed in the last class, in one of the earlier classes, that whatever is the nature or nature of the weight function, if we replace that weight function by the unknown, then that will be a primary variable. So, these are my PVs, primary variables. Then the coefficient of primary variable terms help us determine what are the secondary variables. So, here I have V is the primary variable associated term, its coefficient is B W prime prime. So, this is my secondary variable, and physically this represents shear force, right, it represents shear force. The second coefficient we are talking about is B W prime prime. So, this is another secondary variable, and this represents moment. In your solid mechanics or in lectures, you would have seen that EI, B represents EI times second derivative of W is moment. So, I have two in this problem. This is a fourth order differential equation, this is a fourth order differential, ordinary differential equation, and because of this I have two primary variables, W and its slope, and I have two associated secondary variables, shear force and the moment. Okay. When I integrate this differential equation, because it is fourth order, I will get four constants, and those four constants can be determined if I know four conditions which can be, either I know V or V prime or B W prime prime or the shear force at four different I have to know four conditions using which I can calculate those constants. So, I will call W and minus dW by dx as generalized displacements. As generalized displacements. So, it is not strictly a displacement, because we think displacement as the movement of a point A to another point B, but this is a generalized displacement because W over dW over dx is also a degree of freedom, it is also a degree of freedom. So, that is why, and they are mutually independent. Okay. So, these are generalized displacements, and then these secondary variables and B W prime prime, these are called generalized forces. So, this is a moment, this is shear force, but in a general sense we call them as generalized forces. So, when I develop finite element equations using the weak form, I will have a vector, and in that vector for generalized displacements, and this vector will be on the left side, and on the right side I will have a vector for generalized forces. Okay. So, these are my degrees of freedoms. Other thing I wanted you to remember is that this dw dx, the negative of dw dx is something I am calling it as a primary variable. I am not calling the negative sign is important, okay, because then that makes things more consistent. Why is that important? Because I have said that my q2, which is the moment, is positive when it is moving clockwise. Okay. Same thing about q4. So, I will elaborate on this a little bit further. So, suppose I have a beam and then this beam bends okay. Then the angle, this angle, let us say this is theta, then tan theta is what? Suppose this is the deflection, right, then tan theta will be basically dw over dx, agreed? Tan theta will be dw over dx, but this theta, we are considering that theta is positive if clockwise, right. Now, because this theta is very small, I am taking a very small element, it is a differential element, because this theta is very small, I can call also this thing as theta is equal to dw over dx. But theta is positive if it is clockwise. Now, in this case it is negative. So, that is why I say that my degree of freedom is negative dw over dx. So, it is important, otherwise we will have some errors in our equations based on our convention. So, what we will do is we will rewrite this equation. So, my weak form equation is v double prime b w double prime dx, and all other terms I am taking to the right side, 0 to he. And one thing I did not do, which I should have done, because I am integrating it over an element and this is the local coordinate system. So, this x should have been x bar. So, everywhere you may want to replace this x by x bar. Okay. This is important. So, 0 to he. So, going back, I am going to rewrite this equation. So, this equals fv times dx bar plus, and what I am going to do is all these boundary terms I am going to open this bracket and I will explicitly write down all the boundary terms. So, this is v evaluated at 0 times q1e plus minus v evaluated at v prime evaluated at 0 times q2e plus v evaluated at he times q3e plus negative of v prime evaluated at he times q4e. Okay. So, this is how we are defining q's. So, q1e equals B W prime prime, its derivative evaluated at 0, Q3E is negative of B W prime prime, the whole thing differentiated at HE, and then Q2 and Q4 are shear forces. No, these are moments evaluated at 0, and Q4 is the moment evaluated at like that. Now, we will look at this. On the left side, this term is what? It is bilinear, right? It is bilinear and also symmetric in U and W. So, I will call it as B of L and W. It is bilinear and symmetric. B of sorry. B of V and W. This term, all these terms, this is a linear functional and it is dependent on V. So, this again brings us to our standard form which we had developed earlier, where B of a bilinear symmetric functional was equal to a linear functional. And lastly, we will show that this term is nothing, this entire thing is nothing but the minima of a overall term, we will call it I, and in this case it represents the overall potential energy of the system. So, just consider the term I, and this is for the eth element. So, I have this superscript E, and let us say that this is dependent on W, and I will define it as 0 to HE half B W prime prime whole square dx minus 0 to HE WF dx minus W evaluated at 0 Q1E minus W prime evaluated 0 Q2E minus W evaluated HE Q3E, and then minus W prime evaluated HE Q4E. So, I have just written this functional, but look at it. This term is EI times square of slope, right. EI is EI times the second derivative of W is moment, right, and then when you multiply it by W prime prime, which is the curvature, that gives you the strain energy due to bending of a, excuse me, yeah. So, this is the strain energy of a beam which has been bent. Okay. This is the work done by an external force which is distributed, right. The distributed force is what? Over a small element is F times dx, and at that location deflection is W, then this Wf is the work done by on that small element, and if I integrate it over the entire length, that will be the work done by external force which is uniformly distributed. So, this is work done by external distributed force. Okay. These terms which relate to W and at 0 and W at HE. What are these? Q1 is the shear force, right. Q1 we had explained earlier, Q1 is the shear force. If you look at the definition of Q1, this is my Q1, it is B times third derivative of W, and when you go back to third derivative, B W prime prime and then the whole thing, you know. So this is the shear force, and if I have an external point force, shear force, and at that point if the deflection is W at 0, then that is the work done because of that particular shear force, right. So this is work done due to point forces and finally you look at these terms. Q2 and Q4 are moments applied on the at the ends of the element, and what is W prime? W prime represents the rotation because of that. So moment times rotation is again work done, moment times rotation is again the work done. So this is work done due to moments at ends of element, agreed. So this is strain energy, this is the work stored in the system, and these are all work done by external forces. So this, if you add them up, this is the total potential energy of the system, and then if I take its variation, and if the system is in equilibrium, then the variation of this has to be equal to 0. And if I take the variation of this thing, if you go back to our earlier lectures on the variational operator, if you take the variation of this entire thing, you will get this entire expression, this equilibrium equation. So what this equation represents is the first variation of I when it is equal to 0. So this is the overall equation, and what we have shown today is the basic details of the equation and how we formulate it in context of finite element method. And in this particular context, our conventions are very important, which are listed down here. So now what we will do in the next class is, we will now develop element level equations for a beam, specifically the Euler-Bernoulli beam. So thank you very much, and we will meet once again tomorrow. Bye.